Okay. So in the last class, we have discussed about the microwave spectra, how it is coming due to the rotation of molecules, and we will continue the same in this section also. So we are talking about microwave spectroscopy. Or rotational spectrum. Now let's consider an example. For example, one problem we can consider. So the first line that is J equal to 0 to 1 transition in the rotational spectra. The rotational spectra of carbon monoxide is found to be 3.842 centimeter inverse. So in this case, what will be the intermolecular distance? In this case, it is in interatomic distance, that is between that carbon and oxygen. Okay. So what will be atomic distance? This is just an example. So we have here carbon monoxide molecule. So carbon monoxide will be having one carbon atom as well as one oxygen atom will be bonded like this. So this length we have to find out. It's R0. What will be this distance? If your rotational spectra of carbon monoxide is having the value 3.842 in the first transition. The first transition means 0 to 1 transition. Okay. As you know that the transition will be, how this transition will happen? We have different energy levels. So this energy level we are calculating by using the expression for energy. So that we have done in the previous class. If anybody is attending directly to this class, they will not be going to understand these concepts. We have equation for energy in rotational spectra as E equal to h square by 8 pi square I times j into j plus 1. So for j equal to 0, we have energy E equal to 0. Then j equal to 1. For j equal to 1, we have energy E equal to, this will become 2. Okay. This term is going to become 2. So it will become 2. This will become 2 into h square by 8 pi square I, and so on. And if you calculate the same energy in terms of wave number, okay, so then you have to consider nu bar. Okay. Then we have h by 8 pi square, that is IC, into j plus 1 is the wave number equation for the wave number. This also we have done in the previous sections. Okay, so this energy E in joules, this will be h square by 8 pi square I, the j into j plus 1, and the wave number mu bar will be equal to h by 8 pi square I c, j into j plus 1. Okay. So if you are having 3 here, what will be that value? J equal to, sorry, j equal to 2, then E will be equal to h square by 8 pi square I. Then we have this, here we have 2, j equal to 2, so it will come 2 into 3. So this will become 6. This has to be multiplied with 6. And j equal to 3, we will be having E equal to h square by 8 pi square I into, this will become j equal to 3, so 3 into 4, that is 12, and so on. So if you convert this energy into, if you want to convert these values, so these are in joules, so these are in energy in joules. But if you want to convert these values into term B, this is your B value. This also we discussed in the last sections. So this is your B. So if you want to change that into B, then this will become u bar is equal to, if you consider here, I will just say this in terms of B. Okay, so this is the same energy I'm saying here. So this is the same energy in terms of B. This is not the spectra. This is coming out after that transition. Instead, we have, or I will just replace this mu bar with E, because it may get some confusion. This is also saying E is E, and this E is in centimeter inch. So this is in wave number. In terms of wave number, I'm saying. So each energy level we are representing in terms of B, in terms of B. Okay, that's why I'm putting it like this. So this also representing the same energy levels in wave number. I will test something like E bar, so that it is in wave number. Means the energy levels we are representing in different p values. Okay, so this will become for j equal to 0. For j equal to 0, this will become b into 0. So this is 0. Then this one, the c bar will become that is j equal to 1. So this is 2 times b. Just substitute J value equal to 0, 1, 2, 3, etc. in this equation. Then we'll get like this. Then here we'll get E bar is equal to 6B. Then we have E bar equal to, what is that, 12B, and so on. So I'm just representing this quantity in terms of B. So for that, I have to divide that energy with Hc, so that our unit will become in centimeter inverse. But still, I am representing same energy levels in terms of B. Okay. So how these energy levels will be? So that you can denote these energy levels. First, you have that 0. Let's consider this is your 0 state, 0th energy level. Then we have the next one, that is 2B. This is your 2B. Then you have next energy level, which is 6B. Okay, so 2, 2, 6, here you have, so this is your 6B. Then you have 12B, and so on, etc. So these are energy levels which are represented in terms of centimeter inverse. I don't think that these energy levels are in joules. Whatever you are representing with B, which will be in centimeter inverse. Okay, so these are the energy levels in centimeter inverse. And then if you consider the transitions, the transition will be the transitions. So if you're having transition from 0 to 2B, you're having transition from 0 to 2B. And then you can have a transition from 2B to 6B. This is also possible. Then we have transition from 6B to 12B. So what is the selection rule for this transition in rotational spectra? Selection rule for transition in rotational spectroscopy implies delta J, which is equal to delta J is equal to plus or minus 1. So in each case, you are having J value. Here we have J value which is equal to 0. Here we have J value which is equal to 1, 2, 3, and so on. Energy level we have noted here. So these transitions are possible from 0 to 1, or 1 to 0 also is also possible, or 1 to 2. Similarly, 2 to 1 also possible, and 2 to 3. So the delta J, change in J value, that is delta J, that should be equal to plus or minus 1. That is the condition for rotational transition. So when this transition occurs, we have different spectral lines which will come out from that particular atom. In this case, it is carbon monoxide. So then we will be having different spectral line. For example, if it is going from 0 to 2B energy level, then we have spectra at this point position. Then in the second case, from 2B to 6B, then we have another spectral line, which is like this. And if it is going from 6B to 12B, then we have the next spectra, which is For that case, we have the next spectra here, and so on. So for each transition, we will be having a different spectral line, which is coming out from that particular molecule. And these spectral lines will be in microwave range. So all these spectra will be in microwave range. That's why it is called as microwave spectra. And these values of this spectral line in centimeter inverse, this will be 2B, this will be 6B. How you can calculate that? Takes difference between these two energy levels. So 2B minus 0 is 2B. Then 6B minus 2B. So, okay, this is 4B. 4B. 6B minus 4B, that is the energy difference. So we are considering here it is in wave number. So we can directly write that values in here because we are considering the spectra which is coming out also in terms of wave number. So this is in centimeter inverse in this scale. This x-axis is in centimeter inverse. And next one will be 12B minus 6B is the energy difference in terms of centimeter inverse. So that will be 6B. So this line will be at 6B and so on. So it will be 2B, 4B, 6B, etc. So the difference will be the difference between these two adjacent spectral lines will be always 2B. So this difference will be 2B. Always it is 2B for pure rotational spectrum. Okay. Now coming back to this problem, we have carbon monoxide, and in the it is found that from J equal to 0 to 1 transition, we have the rotational spectra, that first line which is coming at 3.842 centimeter inverse, which means that this particular line, this is the first line which is corresponding to the transition 0 to 1 here, this transition 0 to 1, J equal to 0 to 1. For that transition, we are getting this particular spectra, which is in the green color, and which is observed at 3.842 experimentally. Now, what will be that inter atomic distance? Okay. കേൾക്കുന്നുണ്ടല്ലോ അല്ലേ? കേൾക്കുന്നില്ലേ?
കേൾക്കുന്നുണ്ട് സർ.
So we are considering here the problem of carbon monoxide, which is first transition from J equal to 0 to 1. It is observed as corresponding to this particular spectral line at this position, 3.842 centimeter inverse. That means this green line, this is coming at 3.842, and centimeter inverse, that is in wave number. So see observed data, then we have to calculate what is the interatomic distance, which means that what is the distance between these two atoms, carbon and oxygen. So in that case, what we have to do, we have to substitute 2b equal to 3.842, because you have this 2b value here. Correspondingly, we are getting this 3.842. So 2b will be equal to 3.842. Then b will be equal to 3.842 divided by 2. Okay, so that will be 1.921. Now, what is this moment of inertia? I can write I equal to h by 8 pi square b into c, plus b is equal to h by 8 pi square ic. So if you take I into this other side, then I can write I equal to h by 8 pi square bc. Now this h by 8 pi square c is constant. Okay? And if you substitute this value of b in that particular equation, then you will get this is equal to 14.569 into 10 raised to minus 47. This kilogram meter square is the unit of moment of inertia, mass into r square. So this is the moment of inertia. Now, but moment of inertia I equal to mu into r0 square. Okay, and what is this mu? Mu will be equal to m1 m2 by m1 plus m2. All these things we have discussed in the previous class. So those who attended that class may not be able to catch these equations, but they just follow these steps. So this is the moment of inertia equation I equal to mu r0 square, and mu is the reduced mass, which is equal to m1 m2 by m1 plus m2. Now what is your m1? M1 is the mass of carbon atom, so m1 is equal to mc, that is equal to 12 into 1.67 into 10 raised to minus 27 kilogram. So this is the atomic mass into 1.67 into 10 raised to minus 27. That is the mass number. Then we have M2, which is equal to second atom, that is oxygen, MO, which will be having mass number 16 into 1.67 into 10 raised to minus 27. So after substituting this value in this expression, we will get mu equal to, just check that, 11.3 383 into 10 to the power minus 27. So this is the reduced mass of this carbon and oxygen, that is carbon monoxide molecule. Now if you know mu, then you can easily calculate what is R0. Will be equal to R0 square will be equal to I by mu, or R0 equal to root of I by mu, and that will be equal to, if you substitute value of I and mu, then we will get this value as 1.13 into 10 to the power minus 10, or we can say this is equal to 0.13 amps. So this is the bond length. You can call it as, this is the bond length of carbon monoxide molecule. So this is how we will use the rotational spectroscopy to determine the bond length or the interatomic distance of different molecules. This is the simplest one when you are having only two atoms, and this is the case of diatomic, linear diatomic molecule. In other molecules, when it comes to polyatomic molecule, when it comes to different, for example, symmetric molecule, we have some different complicated equations, but still it is easy. Once you know this spectra, then you can easily find out what is that interatomic distance or bond length of that particular molecule. Okay, so what we do, we will just put your sample. We'll put your sample in some sample folder, okay, like this, and then we will use these microwaves. Microwaves can be generated from microwave source, and it will hit in the sample. And if the rotational energies are or the frequencies are uh, if they match, then they will absorb some of these microwaves. Then we will get absorption spectrum. So some of the microwave lines will be absent in your output, this particular case, and measure which one is absent in that complete possible spectra, and you will get that absorption spectrum. So in that case, you will be having some peak which is absorbed by the molecule, which is in some centimeter. So check what is that particular value. Then you can calculate the interatomic distance. Similarly, if it is emitting some of these microwaves, then you can take the emission spectra and measure that what are the different spectra which are coming out, and then you can measure what is the value of B and calculate the interatomic distance as you can see. So from the spectral output, we can calculate what is the interatomic distance or bond length of that particular molecule. So that is what we do in rotational spectroscopy, and this is the energy levels. These are the energy levels. This particular we have drawn here. These are the energy levels, and the corresponding spectral output for the rigid diatomic molecule. For rigid diatomic. So the word which is the rigid word rigid, it has some meaning because we are considering these two molecules. For example, this carbon monoxide. We are considering this carbon monoxide is having a fixed R or bond length is fixed and it is rotating. We are considering that it is rotating with a fixed R0. But in some cases, this R0 will not be fixed. In that case, we'll call this molecule as non-rigid diatomic molecule. At present, this is rigid diatomic molecule, and we are calculating R0. Okay. And this rigid, as we discussed earlier, this rigid means that the distance between 2 points, which is constant. Separation between 2 points are constant, which is called as rigid. Suppose this is your first point and this is your second point. If this separation is constant, then it is called as a rigid body. this is varying, then it is not a rigid wave. So now we will go to this some more explanation about this rotational spectra. So if you consider any of these rotational energy levels, then the degeneracy of this rotational energy level are given by 2j plus 1. Degeneracy of energy level, which is equal to 2j plus 1. So for example, j equal to 0, if we consider j equal to 0, then the degeneracy is equal to 1, corresponding to that particular value. And j equal to 2, sorry, j equal to 1, then we have 2 times 4 degeneracy will be 3. So the degeneracy of the state of a state in the rotational spectra is given by 2j plus 1. And the number of molecules in a given state j, that will be given by, so number of molecules in state j is, we can say this like nj equal to n0 to 2j plus 1, this is the degeneracy, into e raised to minus ej divided by 8. So with respect to that degeneracy and with respect to this value, we have different number of molecule at level j. Number of molecule at level j will be determined by using this particular equation. So where n0 is the ground state level, and nj is any level which is higher than j equal to 0, then we can calculate by using this equation what will be the number of that particular state or particular level. Now, if you calculate this particular value, actually initially it was thought that only this e raised to minus ej by kt is going to affect this nj, but it was not experimentally correct. If you are plotting these values with respect to j, then we will get it like this. So this is your j values, and if you plot only that e raised to minus ej by kt, assuming that, just giving you this short form. So initially it was thought that nj will be equal to n0 e raised to minus ej by kt, and if you calculate that particular case, then you have j equal to 0 here. Then if you substitute j equal to 0 here, particular case, and value of e, calculate value of e at a different j values, then we will get e raised to minus ej by kt some exponential decreasing factor. Exponentially decreasing. So if this j equal to 0, then you have this ej equal to 0, as we discussed earlier, because it will be multiplied with h square, ej equal to h square by 8 pi square I into j in j plus 1. So j will be equal to 0 in the first case in total. So when j equal to 0, this term will become 1, and only nj will become n0. So this is your maximum value. Now next time, we'll be having different EJ. So the EJ value is not 0, then you will get that exponential decrease. So it will be going like this. Now another factor which will affect this curve is that the moment of inertia, because when you calculate that EJ is nothing but h square by 8 pi square I into j plus 1. So this moment of inertia will also contribute to your what is that? This energy. If you represent that in terms of centimeter inverse, then you will be having h square by 8 pi square IC into j plus 1. So this term is nothing but your B. Okay. So with different I, we have different B, which means that if you are having different molecule, you'll be having different moment of inertia correspondingly, and that moment of inertia will change your value of B, and also it will change your value of this energy. So we are representing that in terms of B, just for sake of understanding. So we are just representing in terms of B. So if you are changing this I, it is going to change your energy EJ. So if you are having I1 and I2, correspondingly we have EJ1 and EJ2. So we have different values. At 0, if you are putting j equal to 0, at j equal to 0, EJ1 will be equal to 0. EJ2 also will be equal to 0. EJ2 will also be equal to 0. Why? Because when j equal to 0, you have this quantity which is going to become 0. So whatever I value, it is not a problem because it is not going to affect your system, because when your j equal to 0, this whole term will become 0. But when it will become j equal to 1, then there will be some change. EJ1 will be having some value with respect to your I. And if I take this I1, which is smaller than I2, let's consider it like that, which means that B1, which is smaller than B2, sorry, B1 is higher than B2 because I is inversely proportional to B. From this, if I consider I1 which is equal, which is greater than I2, then my B1 should be less than B2 because B and I are inversely proportional. Okay, so correspondingly, my energy, can write EJ1 will be, what will happen? So if B is larger, my energy also will be larger. So this quantity is less than EJ. And then you substitute these EJ values in your expression N0 into e raised to minus N0 to T. Then the exponential decay, if you are having higher value here, EJ, so EJ2 is having higher value, so the exponential decay will be higher for that case as compared to this. So we will be having higher decay rate here because it will come e raised to minus some high value here when you are considering EJ2, because EJ2 is larger than EJ1. And when EJ1 is there, then this will be going slowly. So the decay rate will be slow. So with respect to different B value, we have different stop or the exponential decreasing of this particular curve will be different for different B values. So initially we have the it's going like this, first case, and second case it will be going little So this is for B equal to 10. This is for B equal to 5. When B is higher, your EJ is higher, so the decay will be quick. Decay rate will be high, so that it will quickly go to this zero or minimum value. But when your B is smaller, then it will go like this. But experimentally, we didn't get like this, and it is verified that this expansion is not complete. Then we thought about the degeneracy of those states, and we include those degeneracy also in that expression. Then we'll get nj equal to n0 2j plus 1 times e raised to minus ej by kt. And when you include that degeneracy, then your spectra will be coming like this. This is your j, this is your 2j plus 1 into e raised to minus j by kt. You can also include that n0 value, but it is not necessary because you will get some maximum value. Suppose this is equal to some high value 1, normalization of that. And if you multiply n0 with that, this value, then you get the total n0. If you put n0 here, this will become n0. If you do not put this n0, then this will be 1. The maximum you will get this value will be 1. Okay, so that's it. Now, if you plot that particular curve, what we have drawn here at different the value, then we'll get the graph like this. Second one will go higher. We'll go here and so it will go like this. So in this time, you have your maximum value here. Then there is an increasing of the number of molecules in those levels. Then it start decreasing. Similarly, for the other case also, we have b equal to 5. This one equal to 5. This is b equal to 10. Then this one is experimentally also it is coming correct. So at this particular j values, it is having maximum values. We consider j1 and j2. j1 is corresponding to maximum value for b equal to 10, and j2 is the maximum value of maximum number of molecules at this particular j value, that is j2. At j2 we have maximum number of molecules, then your b equal to 5. Okay, then this is experimentally also it is coming in the same way. So then it is found that expression of the number of molecules at the different j values coming as this. We have n0, then we have that degeneracy 2j plus 1 into e raised minus ej by k. Now what will be this maximum population? Maximum population is given by dnj. This nj value should be equal to maximum. So whatever we are having in this axis, this is nj. So if you are plotting this with nj, then you have to multiply this with nj. Okay, when you are in this as nj, then you have to multiply here nj. Otherwise, it is just a normalized value. Maximum is 1, and it is short between 2. So dnj by dj, this should be equal to 0. Then we get the maximum of this curve. So in this point, the variation with respect to j will be 0. Or what we are measuring here, the slope of this curve. Slope of this curve will be dnj by dj, dy by dx. So this dnj by dj will be equal to 0 at this point because it is maximum. So if you measure the slope at the maximum value, we will be having constant y value here. So delta y will be equal to 0. So if you take delta y by delta x, this also will become 0. So that is the maxima of your curve. So dnj by dj should be equal to 0 at this maximum point. So we had to find out what will be the j value at which this quantity dnj by dj equal to 0. Okay. So now you take the differentiation of that value, that is which means that d by dj of n0 to j plus 1 e raised to minus ej by kt. This should be equal to 0. Now, if you use all of the other coefficients and everything, it's at ej equal to s square by 8 pi square I into j plus 1, all those things you have to substitute here. Then you will get the j value at which this condition is valid, that is d by dj of n0 to j plus 1 e raised to minus ej by kt 0. Then you will get j equal to, that is, I will just written as j max, which means that the j value where we will get maximum number of molecules. So j max will be equal to root of kt divided by 2 bhc minus half. So this is the j value correspond to the maximum number of molecules. So root kt by 2 bhc minus half. So you just do this d by dj of this value, then you will easily get this particular equation. So this will be the j value at this condition. So you just differentiate this quantity with respect to j and put that is equal to 0. Then find out what will be the value of j. Okay. So for example, if you want to calculate this maximum population, then as an example, I will just write here for example, for b equal to 2 centimeter inverse, b value which is 2 centimeter inverse, and our temperature is 300 Kelvin. Is the room temperature is nothing but 20 to 73, right? So 27 degrees Celsius. So at 300 Kelvin, what will be the value of, what will the population that for j equal to, for example, for j equal to 1, population means number of molecules in that particular level with j equal to 1. What will be that? What will be? So if you want to calculate, if you calculate that after substituting these values in that expression, then we will get n j by n0. This is what you have to calculate. So this is equal to 2j plus 1 into e raised to minus ej by kt. So you have to calculate ej also here. with the j equal to 1. Okay. Then that will give you this is equal to some point 98. So this will become n1 by n0 this time because j equal to 1 now. Or we can say n1 equal to 0.98 n0. So number of molecules at the level j equal to 1 is 0.98 times n0. That is the meaning of that, which means that 98% of these maximum n0 values, which is in the level j equal to 1. Similarly, you can calculate any values, any number of molecules at a different energy level, j equal to 1, j equal to, etc. So this is the equation that you have to use to calculate the number of molecules at different. Now, as we discussed earlier, whatever we have told is for the case of rigid molecule. What will happen if it is a non-rigid molecule? It is a non-rigid molecule or non-rigid model, or we can say non-rigid rotator. Anyway, so that non-rigid case, what will happen? So when the bond is elastic, okay, which means that that bond length is varying. Whatever we have considered so far is we have one atom here, another atom here. If you are considering that atomic molecule, then they are having some bond length of distance, bond length of R0, and we are treating this R0 as constant. We are considering this bond length is as fixed. But in some case, there will be some small vibration of this molecule or oscillation of this molecule that can be possible. So in such cases, the molecule is no longer a rigid molecule. So this particular atom can vibrate. This particular atom can be vibrating like this. So for example, in some cases, you will be getting R0 like this. And some case you will be getting R0 which is larger than that previous first one. In this case, we will be having that molecule which is here, sorry, that atom which is here. And in this case, you will be having that atom. So your R0 is changing in this case. Your R0 initially it was at this point. R0 was here. Then it is decreased in this case, and it is increased in this case. So in this case, we cannot call this diatomic molecule as a rigid diatomic molecule because it is separation is varying. That bond length is varying or vibrating. That then it will cause the case of non-rigid model or non-rigid molecule or non-rigid rotator. So with this variation in R0, along with this variation in R0, this molecule is rotating. Let's consider with that variation in R0, this molecule is rotating like this. Now what will happen to this rotational energy level? How it is this variation in R0 is going to affect your energy level. That's what we have to discuss. So in this case, when the bond is elastic, when the bond is elastic, then molecule molecule will vibrate, when the molecule will vibrate due to touching and compression of this bond due to stretching and compression of bone periodically. So when the bond is elastic, then molecule will vibrate due to stretching and compression of that bond periodically. And in that particular case, there are two possibilities. That particular vibration that can be harmonic, that is harmonic vibration. It can be harmonic vibration, or it can be anharmonic vibration. Both are possible. Harmonic means that displacement of that mean is going to vary with a constant value. This is whatever your oscillation is coming. That is when the compression is there, then R0 is reducing, and when there is stretching, the R0 value is increasing. So that increasing and decreasing value of this R0, that is constant, that is same. So that it is called as a harmonic oscillation. If it is different, then it is anharmonic vibration. Suppose one side it is going when it is compressing, it is going some different value. When it is when it is in the stretching mode, in that particular side which is going some in a different manner, then it is called as anharmonic vibration. This basically means that suppose if you are having a vibration like this, okay, so it will go in the same magnitude on both sides. But if it is coming back, it will also go with the same magnitude to the when it compresses, and that will produce harmonic oscillation. So that will produce harmonic oscillation. But when you are having the compression and stretching, which is non-uniform, which is not equal on both of that sides, then it is called as anharmonic oscillation or anharmonic vibrations. So if it is harmonic vibration, if this harmonic motion, we consider, I'm considering vibration here, is that vibration, it is, let's say, simple harmonic motion, that vibration is simple harmonic motion, then the force constant for a simple harmonic motion, we know this force constant is K equal to mu times omega square. That will be equal to 4 pi square G mu omega bar square. Your omega bar is nothing but frequency by C. So omega bar, this omega bar is F by C. Or you can say mu by C. Of course, we have to use mu by Freshnel spectroscopy. So this omega bar is nothing but mu by C, where mu is the frequency, C is the speed of light. So omega, 2 pi f. So 2 pi square will come as 4 pi square. Then we have nu. Sorry, we have mu here. Then we have omega bar. Omega bar is nothing but mu by C. So if you take omega bar square as mu square by C square, okay, this is mu bar square, right? So mu bar square if you take, then you have to take square of these things. Then you will get 4 pi square c mu. Then we have nu square here. So 4 pi square nu square is omega square. Then you have mu also. So this one I think have some confusion here because this c, I think we have c square here, right? When you take that square, omega bar square, mu square will come, mu square by c square will come. So only one c will get cancelled. Okay? Here it should be u by square. I think okay, I'll just check this and tell you in the next class. Probably it should come c square, then only this will get cancelled. Or omega bar should have some values. Distortion spectrum. Okay, there will be c square. This is c square. So this is c square times mu and omega bar square. Then this will, if you take mu bars, omega bar square here, then this will come as mu bar, so mu square by c square. Then if that should be here, then c square will get cancelled. Mu square will come, mu square into pi square 4, that is nothing but omega square times mu. So this is the force constant for a simple harmonic motion. Okay. And when that vibration happens, that simple harmonic oscillation happen to this molecule, if it is in simple harmonic motion, that vibration is simple harmonic motion, then we can use this particular force constant to express that particular motion. What is this force constant? Force constant, if you're having a spring which is attached to some mass m, and if this spring is oscillating with the simple harmonic motion, then the force constant associated with this spring is the k value. And as you know, omega, that frequency of this vibration, this will be k by m. From this only we are getting k equal to m times, this will be m times omega square. This value we are using. Instead of m, we are having mu here because it is reduced mass, then omega square. Okay, that is the force constant equation for a simple harmonic motion. And use that particular equation for the case of a molecule which is having this harmonic vibration. So for harmonic vibration, you can write Ej, that is the energy of that particular molecule, which will be h squared by into j plus 1 minus h raised to 4 divided by 32 pi to the power 4 I square r square into k j square to j plus 1. So this is from the quantum mechanics. You have to consider both energies, so for this rotation and vibration potentials. Substitute that in that Schrodinger equation, then solve for energy, then you will get this particular equation. Similarly, what we have done, actually we didn't derive that. I think you don't need that derivation. But for rotational energy also, we have to substitute that value of E, value of that whatever we are getting here. This energy we are actually for rotational spectra means for the case of rigid rotation, we are having this h square by h pi square I j into j plus 1, which is also derived from that Schrodinger equation. Okay, substituting all other values into that Schrodinger equation, then you can find out what is the value of Ej. Okay. So similarly, if you consider the vibration also, consider the vibration associated with that, we have different potential terms which will come, and substitute all those values in your Schrodinger equation, and then we'll get this particular energy for a molecule which is having vibration also with the rotation. Okay. So then you will have this kind of energy with vibration. As you can see from here, this part is from that vibrational effect, if it is harmonic oscillation. Then I can write this, I can replace this with that new bar, or I will just write it as E bar. So different textbook it will be denoted as different. Sometimes it also represent as, okay, I will write both then. It can represent as E bar or it can represent as epsilon. So epsilon is nothing but energy in terms of wave number. So epsilon j, that will be equal to this h square by h pi square IC will come in terms of j in terms of the wave number. So this is b times j into j plus 1. Then here it will come as d, all this correction I am taking as d. Also there will be multiplication with hc. So d is actually d is equal to multiply this entire constant with 1 by hc. We are converting that term into wave number. So this term is multiplied with hc, then it will become h cube divided by 32 pi raised to 4 and I square. Then we have r square k, then c. So this much of terms will be there for d. So this d times j square into j plus 1 square. And this d, we call it as centrifugal distortion constant. Centrifugal distortion coefficient or constant. Centrifugal distortion constant, and its value which is associated with b as e equal to 4 b cube divided by omega bar square. And if it is not harmonic, means that if it is that vibration is anharmonic, or anharmonic vibration, then we have this epsilon j, which is equal to d times j into j plus 1 minus d times, remember this is minus d times j square into j plus 1 square, then plus we have next term as h times j cube into j plus 1 cube plus etc. So we have another constant h, instead of h we have another constant g, then j raised to 4, j plus 1 raised to 4, etc. So for anharmonic vibration we have additional terms also will come to this equation. And this one is called as centrifugal distortion constant. And this is coming from that centrifugal action. Okay, that's why it is called as centrifugal constant, because when you are rotating, you have these two masses which are rotating like this. Okay, then this will always try to move away from this path, and because of that action, and it will come. It is called as that centrifugal distortion constant. So always they will try to uh, have some change in this RC. Anyway, so this is the centrifugal distortion constant, and it is also important when you are considering the vibrational effect, or when you are considering that non-rigid rotator, and this is called as non-rigid rotator case. Energy corresponding to that non-rigid rotator case. Okay. So now what will happen to this energy levels for this non-rigid rotator case? As we discussed, we have, for example, we are considering this harmonic oscillator. We have to consider this harmonic vibration. Then if you consider Ej plus 1, energy difference Ej plus 1 minus Ej, that is the energy level difference between the adjacent energy levels, that will be equal to B into, in the first case we have J plus 1. I'm substituting J plus 1 in terms of J. Instead of this J, we have to substitute J plus 1. So J plus 1 into J plus 1 plus 1 minus next term is, that is for J. So that is J into J plus 1. Then we have that coefficient D, that is minus D times. So this is for J plus 1 state, this is for J state. And D times for J plus 1, it will come as J plus 1 square, because we have J square here, this section. So J plus 1 square into J plus 1 plus 1 square. So it will become as J plus 2 square, right? Minus, then we have J second, that is the second level, that is for Ej. We have same values for J square into J plus 1. Now if you calculate this, then we will get 2B times J plus 1. This you might have got for the first case when we discussed about the rigid rotator case. And with this we have one more term will come, that is minus D into J plus 1 square into 4J plus 4. Or you can take 4 outside also. If you take 4 outside, then it will come as QB into J plus 1. This is for the case of rigid body rotator. We have derived this expression. Then we have minus D. So this is 4, you have to take outside. Then it will come as 4D. J plus 1 square is here. Then we have J plus 1 also come in this bracket. So that will become J plus 1 cube. So this is the energy difference between energy difference between adjacent energy levels in the case of a non-rigid rotator. Means that rotation with along with vibration. And we are considering only harmonic oscillator or uh, harmonic oscillations. And if you draw this particular energy level for this case, non-rigid rotator case, okay, then we have the energy levels. For example, if you consider that rigid rotator, we had energy levels like 0, then we have 1, then slightly it is going to increase, that suppression is going to increase, then 4, I'm not taking the exact values, just showing the schematic. Okay. So this is for rigid rotator, rigid model or rigid rotator. So in that case, we have different transitions. So these are J values, J equal to 0, 1, 2, 3, 4, 5. If we substitute these J values in that energy equation, then we'll get different energy levels like this. Now in that transitions from J equal to 0 to 1, 0 to, 1 to 2, like that, the transition will happen. So transition will happen from 0 to 1, and then 1 to 2, and then we have 2 to 3, then we have 3 to 4, the transition to 4 to 5, and 4 to 5. So all these transitions are possible, and correspondingly we will get this spectral line like this. In each transition we'll get spectral line like this, and so on. So the separation between the first spectral line is at 2b, second one is at 4b, then 6b, etc. This we already discussed. But when you consider that non-rigid model or non-rigid rotator, so for non-rigid case, what will happen? We have 2bj plus 1 here. So so energy level you can see from here. These are your energy level with the distortion constant or with the effect of vibration, and these are your energy levels in joules with vibrational effect. You can see. So you can see that this is minus here. This minus. So whatever you are getting with the rotation, if you are considering only rotation, you are having b into j plus 1 minus this quantity, minus this quantity. So whatever your energy level was before, when we considered only that rotation, it will be slightly decreased. That energy level value will be slightly decreased because of this term, because it is coming as minus d into j square into j plus 1. And also remember that when you go for higher j values, this j square into j plus 1 square will be very small, and this d also very small quantity. So this entire term will be small. It's very small. It will not be having very high value. So this value will be very small. This d is also very small quantity. It will be coming in some point values. Okay. So this values, this entire term will give you some small quantity. So don't think that it will become negative as a dj will not become negative. So this is very small quantity as compared to this term. But still this term will be having will be decreased. This value will be decreased by this amount when you consider that vibration effect also. Means that in non-rigid case, your energy level will be slightly decreased. So if this is your 0, and that 0 will be the same because j equal to 0 case, that is same. This will be in the same line. And from next level onwards, you'll be having a very slight difference, your energy levels. So if this is your energy level without considering that vibration, it will be slightly decreased when you consider the case of that when you include that vibrational effect, or when you consider that non-rigid rotator, it will be slightly decreased. Over here, then we have that third one, the fourth energy level here. Here also it will be slightly decreased. Here. So this will happen to the energy level. Energy level will slightly decrease. And if you consider the transition now, transition selection rules, all those things are same. In this case also, we have that J quantum number only, rotational quantum number, which is J. Only that quantum number is there. So the transition selection rule will be delta J equals plus or minus 1 for this case also. So we have only that quantum number. If we have any additional quantum number, we have to consider different transition. That corresponding to that quantum number also we have to consider the selection rule. But here only we have only one quantum number, delta J. So that only that J variation we have to consider. So here also the transition will have the same case as in this case of that the rotational rigid rotational case or rigid model. But here we can see that energy difference between those energy levels, which is coming, if you consider that spectra, we are having 2b j plus 1 initially. So if you take different j values here, then we have 2b into j equal to 0, which will be 2b. Then second one will be 2b into j plus 1, that is 1 plus 1. This is for j equal to 0, for j equal to 1. For if you are considering only that rotation, which means that if you are considering rigid model, then for j equal to 1, it will be equal to 4b. Then j equal to 2, it will become 6b. J equal to 3, it will become 12b. Sorry, it will become 8b. Okay. This is wave number, the output spectrum. But when you consider this term, when j equal to 0, j equal to 0 means this term will become 0. Then 2b minus this j equal to 0, this is 0. So 2b minus this will become 0. 2b minus 4b. Right? Then we have the second case, j equal to 1. Then we have here j equal to 1 is j plus 1 equal to 2. 2 into 2, 4b will come. Here we have 4d times j plus 1, that is 1 plus 1 cube. So this will come as minus 2 cube into 4. So this is 8 times 4, that is 32. But still this d will be smaller. And then we have next one, and 6d minus additional quantity, which is coming as 4d into j equal to 2. So this will become 3 cube. 3 cube means 9. That is 9. Right? Sorry, 9 into 3. 27 will come. 3 into 3 into 3. That will come 27. 27 times 4. That value will come here. So this is 27 into 4 times d, and so on. I will calculate one more. So 27 into 4 is almost coming, 25 into 4 is 100, and 24 8. So this is 108. That will come as 108 d. The next one will come as j equal to 3. So this will come as 4 cube. So it will come 16 into 4. That is 64. 64 into 4 will come from this side. 4 into. So this is 256. And so on. So from that 2b, 4b, 6b, we have some difference. So if you draw that accurately, then what will be the result in this case? Now if you draw that spectral lines, then we will be having transition. First we will be transitions are same. We will be having different transition in this case also, from 0 to 1. Then we have the other transitions also. But when you consider to that spectral line, it will be first one be here. Then we'll be having some other value. And when we go to those higher values, then the spectra will come close to each other. When we go higher and higher, lines are not constant in this case. For the transition, different transition if we consider, then those transition, it will not be exactly like this. When you go for higher values, higher J values, then it can be observed very clearly. But I have just shown this for the sake of understanding. So in the initial stage, that will not be that much different, but in the final end of this spectra, we will be having considerable difference in this separation of different spectra. Okay. So this is what will happen when you consider the non-rigid model of the molecule. This means that the molecule is having rotation along with harmonic vibration. Okay, so we have all those transitions here, and from each transition we will be having different lines, and these lines, because this from this you can see that 2b minus 4d is first one, and then we have 4b minus 32d. So if you take the difference between these two, that will not be same as difference between these two, because in the first case we have difference 2b, difference between these two, which is 2b. Then we have minus 32 minus 4. So that will come as something 28. Okay, so minus 28. We consider like that. Then we have these two separations. If you consider, then we have 62b again. Then we have this separation also. 108. We have minus. Okay, so we have here 2b. 2 I'm saying. So that will give you 2b. 6b minus 4b is 2b. Then if you take difference between these two, then 108 minus 32b. So that will come as minus, what is that, 108, then 8 minus 32. So 76. Okay. So initially, in the first two spectral line, difference between these two first two spectral line, that means that these two values, this two value I am saying, is j equal to 0 and j equal to 1. So that this two separation between these two, that will be equal to this value 2b into 2b minus 28b. And in the next case we have, next case means j equal to 1 to 2 transition, and we have these two values. And in that case we have the separation is 22b minus 76. So initially we have 2b minus 32a, sorry 28b. Then it is decreased with some around 50D value increased here, so that the next line will be, this is less than that. So if it is X and this is Y, then X is more than that. Because it is having 2D minus 76. This one is having 2D minus 28D only. This is having 2D minus 7060. So this is decreasing. It is less than that of this one. Okay, that's what happens when you consider this non-rigid rotate. So we will continue from here